Thank you very much. I also thank the organizers for thinking of this anniversary, and I think it's a good idea to pay attention to that. And then they thought of asking me to talk about it, and you are going to find out whether that was a good idea. There are actually some people here in the audience that still knew Abraham Robinson. Paulo Riebenboim told me that he met Robinson a number of times, and I know Max Dickman also. And Carol Wood was one of the last graduate students at Yale of Robinson. Maybe there are some more here. I never met him, but I was very influenced, of course, by his work. So I want to give some brief background. His life was not very long, but he accomplished quite a few things during that time. He was a student of Abraham Frankel at the Hebrew University. He was at the Sorbonne, actually, in 1939 and 1940. Was able to take one of the last boats leaving for England from France, was enrolled in the French Free Air Force, and then went to the English, the Royal Air Force, I guess, and worked on aerodynamics without any degree, of course, but he became a real expert in this subject. And, but he already had written some papers on algebra and logic as a student. So you can see there his academic positions. He was at the Cranfield College of Aeronautics right after the war, and then at the University of Toronto in applied math, and actually was the chair of the department there. Later on, then at the Hebrew University, at UCLA, he actually had a joint appointment in mathematics and philosophy, and then went to Yale University. Well, you can already guess that he reigns widely in his scientific work from pure algebra. That's where he actually started. Then he had his career in aerodynamics and related issues, and to model theory and its applications, including non-standard analysis, of course. Also papers on summability, computer science, philosophy, and history of mathematics, and exposition. Among other things, he wrote 9 books. So, well, I'm not expert in all these things, so I will just talk, I will focus on the model theoretic side, and I think one can say that his remarkable vision has over time greatly influenced the course of events, as this IHP trimester has shown, I think. Okay, so I want to mention some literature around him. Well, there are his selected papers in 3 volumes, edited by Kiesler, Körner, and Luxemburg, and Young, including also a volume on applied mathematics, and the other 2 volumes are on algebra and model theory and non-standard analysis. There are 2 very nice obituaries. One in the bulletin of the London Math Society and one by McIntyre in the bulletin of the AMS, which I certainly recommend reading. There's also a book by Dauben. I have some views on that. And Dauben also wrote a biographical memoir for the National Academy of Sciences. Okay. All right. Yeah, so let's now get, before I start actually talking about his actual work, I still want to make a few general remarks. because when he started his work, I think one could say that the standard attitude among mathematicians was to view logic as foundational and as a kind of hygiene, but not assign to it a more glamorous or creative role, such as, for example, geometry clearly has in the mind of in the mathematical mindset. Now, I think one could compare this attitude to the attitude of many people who think of mathematics as a kind of, number crunching or drudgery that computers can now do better. But, Robinson certainly saw a lot more of it, more in it than that. So his ambition, I think, was to show that logic could be really useful and flexible as a tool in mathematics, like, for example, algebra is, and actually enable creative moves. So that is what he set out to do when, after the war, he began to work again in logic. So in the beginning, he combined model theory and algebra in a novel way. And later, he intended also to show the relevance of model theoretic ideas in analysis and number theory. And of course, he was in the middle of doing that when he died, tragically. So, so now, of course, we have seen here many times that model theory now interacts with virtually any kind of mathematics. But when Robinson started, maybe only Maltsev and Tarski had an inkling that the subject had a future. Perhaps someone knows some other people that were positive, that had some positive ideas in this direction, but those are the names that come to mind. Maybe one could think of Skolem, but Skolem was a little pessimistic, perhaps, because he had proved the Skolem-Löwenheim theorem, which seemed to be a negative thing. But anyway, before I get to that, one should also say that Robinson was clearly influenced by his experience as an applied mathematician. I mean, if you look in his book on non-standard analysis, there are all these subjects that he discusses that clearly have an applied origin. And by his general outlook on mathematics, where I think he evolved towards formalism, with Leibniz as an inspiring figure. Leibniz said things like, not exactly this, but things in the direction of infinitesimals don't really exist, but are useful fictions. One can use them, use them to prove things that don't mention infinitesimals, then you can be sure that they are true. I'd heard about Robinson's formalism before, and I didn't really believe he was a formalist, but after reading, preparing for this talk and reading things he wrote about it, I actually think he was quite serious about that. Okay, so I want to set the stage a little bit because, he started not from nothing. I mean, in 1945 there was already a certain amount of, certain number of ingredients around in model theory, except that people, I think, did not put it under one roof of model theory. It was just isolated results in logic or isolated packages that people didn't really connect into one subject. So there was, of course, the Löwenheim-Skolem theorem and Skolem's non-standard models of set theory and arithmetic. And I believe that Skolem viewed this as showing a limitation on the axiomatic method, as negative. Yeah, the fact that you can prove there is a countable model of set theory, of ZFC, assuming that it's consistent, showed, I think, to Skolem that somehow there was something wrong with axioms for set theory. Now Robinson, of course, later saw it as an opportunity to further exploiting this method. So there was already back and forth, but used by Hausdorff in rather special problems about ordered sets, and the nature as a general model theoretic device, I think, emerged only in the 50s by people like Fresse and Ehrenfeucht. So I don't think people realized the relevance of this method at the time for model theory. Well, model theory wasn't even named yet. I think the name only arose in the 50s. Then, of course, you had first order logic, where I can think of at least these three names. There was logic already, but I don't think there was a clearly defined fragment of logic that was isolated as first order logic, and I think these people are certainly responsible for doing that and singling it out as an important part of logic. And then, of course, there is the completeness and compactness theorem that, in some sense, presuppose first order logic. And Maltsev even started to apply compactness as a tool in certain algebraic settings, mainly in connection with groups, I think, in the early 40s. You also had universal algebra by Birkhoff, Maltsev, Tarski. In fact, later on in the 50s, I think model theory was thought of as universal algebra plus logic. I think now we certainly consider it as much richer. But it certainly had an influence on the development of early model theory. And then you had quantifier elimination. People like Tarski, Skolem, and their students did that. But they mainly saw it, I think, as a tool to prove completeness and decidability of first-order theories, rather than as a tool to reveal the nature of definable sets. And of course, that it can reveal the nature of definable set is really what counts for a lot of applications of this technique. And then, of course, there was Tarski's truth definition, which was presented in a rather philosophical style. So I'm not sure how many mathematicians took that seriously. Okay, and then there were other things around that I think somewhat isolated things, but that turned out later to be quite relevant, like Ramsey's theorem, Hebrand's theorem, stone representation theorem for Boolean algebras, ultrafilters. They were all there, but I think their role in model theory only came considerably later. You can see from some of these names that some of the sad history in logic. I mean, Ramsey and Hebrand both died very young and could have contributed a lot. But anyway, right. So now, let's now start with Robinson's first early work. So I just took these three things: transfer principles, diagrams, and bounds. So transfers are things of this kind. Yeah? If you have a sentence in the language of rings, which is true in the field of complex numbers, then it must be true in all algebraically closed fields of, except for finitely many prime characteristics. And I mean, this is just one example, but there are plenty of others. And Robinson pointed out a number of applications of this and also other cases of this kind of transfer principle. Right? And of course, there are really some very nice examples nowadays, like, for example, X's theorem about if you have a definable bijection, a definable bijective map from a definable set in an algebraically closed field onto itself, then it is automatically, oh, wait a minute. if you have an injective map from a definable set in an algebraically closed field into the same definable set, then it must be bijective. And there are other very nice examples okay, diagrams. So that's really due also to Maltsev. Maltsev and Robinson observed that an extension of a group, a ring, or more generally any structure, is essentially the same as a model of a certain theory, namely a model of its quantifier-free diagram. Yeah? Which is basically like the multiplication table of the structure. So that means that for a structure to embed into a model of a given theory is the same as T extended by the diagram of the structure having a model. And by compactness, this can be reduced to having to the property that every finite subset of this extension of T has a model. So this simple idea has many variants. If you consider not just embeddings, but elementary embeddings, then of course you have to use the complete diagram. And if you are interested in homomorphisms of a given structure into the models of a theory, then you need only to consider the positive quantifier diagram. So I think you can see that this brings a host of issues under the umbrella of model theory, at least in principle. I mean, this is definitely a technique that we use without even realizing it nowadays, I think. But someone had to start it. Bounds. Right. Yeah, this is something very much in the Robinsonian style, and yeah. Nowadays, of course, things like the Neustellensatz and lots of other results in commutative algebra have very efficient proofs, but these proofs often, yeah, for example, using Noetherianity and so on, but these proofs often obscure the existence of uniform bounds. And one thing that Robinson realized was that they could be recovered almost without any effort from the results themselves by merely observing the first order nature of certain concepts and then applying compactness. And sometimes one obtains bounds. In the case of Hilbert's 17 problem, the existence of bounds, uniform bounds, was proved for the first time in this way by Robinson. Yeah, maybe I should give an example. The simplest example is maybe the Neustellensatz, where you ask, given, let's say, k polynomials in n variables, when do they have no common zero? Well, we know by the Neustellensatz that this is the same as saying that one can be written as a linear combination of these polynomials, and the bound that there is a bound there on. So if the polynomials are f1 up to fk, and if they don't have a common zero, then 1 equals summation gi fi, where the gi's, the degrees of the gi's, can be bounded purely in terms of the degrees of the f's and the number of variables. Yeah? That is a typical uniform bound, which is not obvious from at least not obvious from the modern proofs of the Neustellensatz. But the fact that having no common zero is a first order property, and the fact that being a linear combination of f1 up to fk is a disjunction of first order properties, yeah, and then the first order property being equivalent to a disjunction of first order properties means by compactness that it's equivalent to a finite disjunction of these properties, and that gives you immediately a uniform bound. So this principle can be used over and over again, and there are, yeah, I could say a lot more because I was quite interested in these things myself for a while. I still am, but I think I'll continue. So yeah. Okay, so this is one of the inventions of Robinson that we use all the time now. Probably every second talk at this IHP meeting mentions something like model completeness or something in this direction. And that is, what does it mean for a theory to be model complete? Simply means that if you have two models, M and M is a substructure of N, then M is an elementary substructure of N, which means that all statements with using parameters from M is true. Such a statement is true in M if and only if it's true in N. So, yeah, as I already said, this Robinsonian notion is now ubiquitous in lots of things we do. And in fact, to apply model theory, we often begin with proving that a certain theory is model complete. Yeah. I mean, for example, a beautiful example is Alex Wilke's theorem of the model completeness of the real exponential fields, which really uses this notion and the test for proving it. Yeah, Robinson's complete theories from 1956 is actually my favorite among his books, and it develops the generalities around this notion and contains this very useful test, namely that the theory is model complete if and only if for all models of it, M and N with M as substructure of N, we have that M is an existentially closed substructure, which means you only have to check for existential sentences with parameters from M, that if it's true in M, then it's also true in N. So that reduces the problem of model completeness to something very basic about solving systems of equations and inequations, basically. If you can do it in M, you should be able to do it in N. Right, and of course this is related to quantifier elimination. By Tarski's quantifier elimination, the theories of algebraically closed and real closed fields are model complete. But Tarski's original proofs, while very direct, are, I would say, cumbersome. It's all explicit, and so you could say that has advantages too, but it takes quite a lot of case distinctions. And so Robinson's used his test to give beautifully transparent proofs of model completeness for these structures, and also derived the solution of the Hilbert 17 problems from it in a few lines. And also with several new variants where, of course, Hilbert 17 problem, maybe I should remind you, is whether every positive definite polynomial on the reals in several variables is the sum of squares of rational functions. Right, so, and then you can ask if the polynomial is in n variable and you have a bound on the degree, can you bound the number of squares and the degrees of the numerator and denominator of the rational functions? And indeed, that follows from compactness using Robinson's arguments. And the variants I have in mind are things like where you take polynomial functions not just on Rn, but on, let's say, a subvariety, or even just some definable set. There are all kinds of variants that immediately follow in the same way. Yeah, so one thing that really was exciting to me at the time, an eye-opening proof in that book, Complete Theories, is where he establishes the model completeness of the theory of algebraic closed valued fields and classify them up to elementary equivalence. And yeah, somehow, I think I found this out on my own. I mean, I had already learned about X-Coach and Yeshov, but then I found later that Robinson had actually done something in this direction before. And I thought this was really very nice. yeah, but it was certainly overshadowed in the 60s by Ekskochen and Yershov, but the participants in this trimester know that it really has made a comeback. I mean, this result is now used all the time, for example, as a starting point for motivic integration in the Hrushevsky-Kazhdan style. And so this is definitely still very much alive. Right. Yeah, one thing he didn't do was looking at the definable sets in such valued fields. In fact, this is one somewhat surprising thing that you don't see that much about definable sets in his work, although there is one example where he did prove an interesting fact about definable functions in certain structures. Right, so one nice advantage of model completeness over quantifier elimination that it's more robust, linguistically more robust than quantifier elimination, but of course it's a bit weaker. So, but Robinson did realize soon that he could prove T to admit quantifier elimination as well by model theoretic means. Basically, you have to show that T is a model completion of a certain universal subtheory. So that appears in a later paper. And then, in fact, if you look at his proofs of model completeness, they could easily be adapted or extended a little if you take, of course, the right primitives. Because one typical thing about quantifier elimination is you have to choose the right primitive to do it. So this, of course, led to model theoretic tests that are also very much used by Schoenfeld and Bloom, such as a theory admits quantifier elimination if for all models M and N, any embedding of a substructure A of M into N extends to an embedding of M into some elementary extension of N. So this basically reduces doing quantifier elimination of proving to doing algebra or extension theory for structures in a certain category, and somehow that reduces the work a lot. And there are still other tests. There is the sort of geometric tests for proving quantifier elimination in structures like difference fields and differentially closed fields. But I think I'll continue now. So this is not the end of the story. In the late 60s, Robinson actually returned to the general theory around model completeness by introducing a useful generalization of model completion, namely the so-called model companion of a theory, which may exist or not. And if it exists, that's very nice. And then also the allied notion of a model of a theory being existentially closed. So one could, for example, an inductive theory has a model companion if and only if the class of existentially closed models of it is an elementary class. Right. So he also introduced what he called model theoretic forcing and generic models of theories. And well, Isaac Goldbring told me that this model theoretic forcing in a continuous model theory setting is very useful to construct certain C-star algebras, and that there is no other way known to construct them. And of course, there is also the notion of an existentially closed group and existentially closed Q fields which have been studied. So this definitely had a lot of follow-up. Okay, now still a few more things from the 50s. And in fact, I think there are plenty of things that one could mention. Some of them without very much echo or follow-up so far, but here are two that I like. So with Lightstone, he proved that the definable function in an algebraically closed field of characteristic 0 is piecewise rational, where the pieces are constructible sets, or if you like, quasi-affine subvarieties of affine space. So in positive, yeah, I think they only considered characteristic 0 there. In positive characteristic, you have to allow p to the nth roots of piecewise rational functions, right? Because the pth root is a definable function there. Yeah, one feature of the proof that is a little curious, perhaps. It's very direct and explicit, but and therefore takes 14 pages. And so it's not done in the Robinsonian style. So with Robinson's own method, this is proved nowadays in a few lines as a corollary of the Galois theoretic fact that definably closed subsets of an algebraically closed fields are exactly the perfect subfields. So, yeah, another thing that is certainly well known and that also has had a lot of follow-up, is the solution of Tarski's problem on one of the problems that Tarski posed in his monograph on the field of real numbers, on the elementary theory of the field of real numbers, is what happens if you add to the field of real numbers a primitive or a predicate for the subfield of real algebraic numbers. Is it still decidable? And so Robinson solved this as a consequence of proving model completeness for the theory of real closed fields with a distinguished proper dense real closed subfield. But you have to be careful in the language. It's not model complete just in the language of ordered fields with a predicate for distinguished proper dense real closed subfield. You also have to add predicates for linear dependence over the subfield. Right. Yeah, lots of further work has been done in this direction. People have introduced beautiful pairs and more general dense pairs, and still going on. Of course, there is now a lot more to investigate. At that time, the main question that people were interested in was these things like decidability. Is the structure decidable? But now, of course, we want to know really more how the category of definable sets in such a structure behaves. Yeah. Well, actually, going back to the first thing with Lightstone, this is one of the cases where he did pay attention to what is definable in a given structure. What are in this case, the definable functions, right? But otherwise, you don't see it that much in his work. And of course, yeah, nowadays we always want to find out for a nice structure what are the definable sets. Not only the definable sets, what are the definably closed sets in a structure, because that gives automatic good information about what are the definable functions in such a structure. Okay. Right, and then I come to differential fields. So in the late 50s, Robinson realized that some work by Seidenbergs on differential fields of characteristic 0 implied that the theory of these structures has a model completion. The models of this model completion he called differentially closed fields. And of course we have been hearing about this already a lot. And this has indeed been a seminal invention, though it took time, I think. There's so much to say that I won't do it, especially about the intriguing stability theoretic properties of differentially closed fields that are used in Diophantine geometry and on and on. And I'm just listing here a number of people who got involved, but one could extend the list by many more names. yeah, one thing, he did not actually prove that the theory of differential fields has a model completion by his own methods. He simply took the Seidenberg work and saw that it gave you that with a little more, with a little bit of model theory. So, but for example, Lenore Bloom was the person who then used the more Robinsonian way of proving that, and by also coming up with nice axioms for differentially closed fields. In fact, I don't think that Robinson actually gave clean, nice axioms. He just showed that they existed. Right. Good. Yeah. Well, I should say Robinson himself did return to differential algebra in some of his late papers on Hardy fields and local partial differential algebra. Yeah, the last two, the local partial differential algebra, I haven't really read very much, but the two papers on related to Hardy fields I found very suggestive. And in fact, in my work with Aschenbrenner and van der Hoeven, it inspired in some sense the notion of an H field and the conjecture, which is now proved, that the theory of H field has a model companion. So you could see that in one of these papers he was really trying to find an element, let's say elementary axiom for Hardy fields. He didn't quite get, basically he showed that the axioms he had were not enough. But right. Oh. Yeah, so now I come to non-standard analysis, which is what he started to do in the early 60s. And just to explain for those who haven't heard about this, if you pass to a sufficiently saturated elementary extension M star of a structure M you are interested in, then you automatically add lots of ideal elements. And this may suggest new tools to study M, the structure you are interested in. For example, when M has among its ingredients the field of real numbers, as for example given by a sort or whatever, then R automatically gets extended in M star to a bigger ordered field, R star, which contains infinitesimals, with a natural map back to the reals, which assigns to every bounded element of R star the nearest real number, which is called its standard part map, or its standard part. The map is called the standard part map. So Robinson realized in the early 60s that this could be used to develop parts of mathematics in a new way, and he put a lot of effort in that. And thus emerged his non-standard analysis. And he saw it also as a vindication of Leibniz's ideas in using infinitesimals and other ideal elements. Yeah. So I think this fits perfectly in his general approach to applying model theoretic ideas. But there are, of course, some novel aspects compared to what he did in the 50s. But to see it as somehow superior to his other work, or its culmination as it's sometimes presented, that it never struck me that way. But I mean, it's very natural and should certainly be pursued. But it takes experience and sensitivity to see where a non-standard approach and model theoretic ideas in general can make a difference. It's not a panacea. It's not a panacea. I hope I'm not saying something controversial here. Okay, I want to make, yeah, from a logical point of view, there is a novel aspect because the structure of interest could be of higher order, right? Ordinary mathematicians always work with higher order structures in a natural way. If you have, if you consider a ring, you also consider the ideals in the ring and so on. But basically, he simply treats them as first order, using, for example, the power set of the reals as a new sort on the same level as R itself, with the membership relation as relating the two sorts. So in what I sketched above, the standard part map is a good example of something that is very useful, but it's not definable in the ambient M star. And Robinson called it an external map. Actually, now I suppose we could see this as some kind of hyperdefinable object, right? The equivalence relation between two real numbers of non-standard real numbers of being infinitely close is not definable, but it's an intersection of countably many definable sets, and that one can already do a lot with just that. Now, yeah, using this kind of setup is now really second nature to many of you. Yeah, and the subject did attract a lot of attention beyond model theory. That's one of the good things in it. In analysis, for example, mathematical physics and probability, several people wrote books. Dynamical systems, algebra and number theory, Roquette. I'll come back to that last area. So I want to mention just one little book using the non-standard approach by Ed Nelson, which I think is a very nice little book. It's called Radically Elementary Probability Theory. I think he basically tries to show that if you start from finite probability spaces and take and lift it to hyperdefinable, hyperfinite probability spaces, you can basically recover full probability theory. So the measured theoretic complications that often there often are in probability theory simply disappear. So yeah, and another thing that I want to mention is there is something called Loeb measure, which is a very widely used non-standard tool, which almost trivializes the construction of useful measures in many situations. Okay, Robinson-Roquette. Yeah, so here I try to describe the basic idea. So Robinson had high hopes to make his non-standard methods effective in Diophantine geometry. So to give a very rough idea, suppose we want to know when a Diophantine equation fxy is 0 over q has infinitely many integral or rational zeros. So f here is a polynomial, and in fact I'm going to assume without loss of generality for this question that it's absolutely irreducible. We also, of course, now we know that to have infinitely many rational zeros forces the genus of the curve to be either 0 or 1. But at that time, the Model conjecture was still open, I think. Yes, no, I'm sure. But also, if you look at integral zeros, there was the theorem of Siegel that if you have infinitely many integral zeros, the genus has to be 0. And not only that, but satisfies some further conditions. Anyway, this is already an interesting situation to try to understand from any point of view. Right? So why not from a non-standard point of view? So Robinson argued this way: suppose it does have infinitely many zeros, then you have a generic 0 over q, xi eta, in an elementary extension q star of q, and we can simply identify the function field of this curve, of the curve fxy is 0 over q with this subfield q xi eta in q star. And now q has a very rich arithmetic structure, and it simply lifts to q star. Yeah, q star inherits from q an enormous amount of structure, plus it is reasonably saturated. So it has further structure that Q doesn't have. But then you can restrict again to Q Xi eta, and so going from Q to Q star and then going back to Q Xi eta, you also get a rich structure on this function field. And so, of course, one could simply try to profit from that. I think this, as a general idea, this looks very interesting and potentially very, productive. But let me be a little bit more specific by looking at the valuations on these function fields. Yeah, I mean, the valuations on the function fields give rise to a divisor theory on the curve, and the valuation. But you also have valuations that correspond, valuations on Q star on this elementary extension coming from prime numbers. There are two kinds. There are non-standard prime numbers, infinitely large, and finite prime, the standard prime numbers, and they yield valuations by restricting to Q Xi eta valuations on this function field. In other words, valuations that are trivial on Q. Now the standard primes, this is not quite true, but it is true if you suitably coarsen, right? If you mod out by the value group by the convex, by the multiples of the valuation of the prime number, then you get also valuations on these function fields. And in fact, it's even true for the usual absolute value from, if you take the usual Archimedean absolute value of Q lifted to Q star, and then you can use that to define a valuation on the function field Q Xi eta. So basically, the arithmetic of Q lifted to Q star induces on Q Xi eta a divisor theory. And then the natural question is, how is it related to the already given divisor theory of Q Xi eta as a function field? Right, so this is a starting point, and Robinson and Roquette followed it up by proving the Siegel-Mahler theorem in this style. So there is a lot more one could say about this approach. One thing is that it gives a better, first of all, for simplicity, I just took Q, but everything I said is also true for a number field. So it has given new results, not particularly in this direction, although it gives you good insight in how effective the result is. But there are some new results, for example, on which fields are Hilbertian. Yeah. Some student of Roquette wrote a thesis about it, which I think is very nice, which gives new results of proving, for example, that the maximal abelian extension of the Q is Hilbertian, satisfies the Hilbert irreducibility theorem, and things of this kind. Right. Yeah. I don't think there are now, of course, many applications of model theoretic IGs into Diophantine geometry, but it hasn't quite followed this this plan. But maybe something that comes reasonably close, I think, is this work of Ben Yakov and Husovsky. But they work in a continuous logic setting. And the big advantage there is that one can express the product formula in first order terms, right? This is something that Uri also mentioned, and I think this is, that is something that was not present. I mean, Robinson, of course, was very aware of the fundamental nature of the product formula and the fact that it couldn't be expressed in ordinary first order logic. But now it seems we can, so this looks a very interesting direction. Okay, so now here is an area where H5 stands for Hilbert's fifth problem. So this is one area where I think a non-standard approach has really paid off. So Robinson actually said something about Lie groups. Here the direct use of infinitesimals is altogether natural, right? But of course, Lie group theorists already have their own infinitesimals, which are basically derivations generating, how do you call them, one-parameter subgroups. But if one is looking for an area in Lie theory where these very general ideas about infinitesimals could really play a role, then Hilbert's fifth problem is a good place to look at. Which topological groups are Lie groups? So this was solved, this question, in the early 1950s by the combined efforts of Montgomery, Zippin, and Gleason, and also Yamabe made a very important contribution by showing how to approximate arbitrary locally compact groups by Lie groups. So the full story is rather lengthy and fills a book by Montgomery and Zippin. And in the early 1980s, Gromov used these deep results in his beautiful work on groups of polynomial growth. And also less well known is that in the 1980s, Hirschfeld, who was one of the graduate students of Robinson, although I think the problem that Hirschfeld described it as finally doing his master's thesis at an earlier, which he did at an earlier stage of his career before he went to Yale. Anyway, he gave a nice non-standard treatment of H5, which was later improved by Isaac Goldbring, who then also settled the local form of H5 that was still open. And then also around that time, I think, Tao and others started work on the structure of approximate groups. And Khrushchevsky realized that this issue is closely related model theoretically to H5, even to its local form. In a sense, these issues are all very intimately connected, but you really only see the connection if you use model theoretic IGs. So eventually this led to definitive results, including various improvements of Gromov's theorem, and you can read this very nice paper by Bruyère, Green, and Tao, The Structure of Approximate Groups. They use non-standard analysis there, but in the guise of ultra products. I mean, Tao is someone who likes to work that way, I think. Okay. Oh, I've already exceeded the time, but I'm almost done. In fact, this is my last slide. Yeah, there's one paper that I hope if you haven't read it yet, you will. It has the title Meta-Mathematical Problems, appeared in a JSL 1973. And it gives maybe the best impression of his model theoretic interests, what motivated him, and the hopes that he entertained for further developments. Some of the problems he lists are still wide open to my knowledge. For example, the issue of uniform bounds in differential polynomial algebra. I mean, in ordinary polynomial algebra, you have questions about ideal membership and things like that, where you do have uniform bounds, but some of these questions are still open in differential polynomial algebra. Anyway, I think it's a list of 10 problems of very different nature, but this is one of them. Yeah, and then a few remarks about what happened afterwards. Around the time of Robinson's death, the Shelach revolution in model theory was taking hold, and it almost overwhelmed the subject and had different, more purely internal motivations than those typical for Robinson. But as this trimester has shown, the fundamental new ideas that have come to model theory after Robinson are perfectly compatible with his general outlook and interests. And at that time, there was definitely a split between East Coast and West Coast model theory. But this has, I think, one could say that it has been replaced by a synthesis to which people from both traditions have contributed. And I think that Robinson would be very pleased by that. And yeah.